Okay, we're going to look at the applications for the work on centrifugal acceleration. So if we look at things that are going at constant velocity, where they're going in a straight line at a steady speed. So it might be a car going on a flat road at a steady speed. What are the forces that are going to act here in this situation? Well, to start with, you actually could draw this thing through here as a road. There's going to be a force of gravity on this car. So you can call it the force of gravity, or you could also call it the weight. Okay? But it's going to act downwards. So the force of gravity is going to act downwards on the car due to its weight. There is a reaction force to that from the road going up here that you could draw, which is going to go up through the road at 90 degrees, and that reaction force is called the normal force. Okay? So you've got a gravity force or a weight force there and a normal force. Now they will be equal and opposite in direction, and we know that because the net force up and down has to be zero because the car's not moving up off the road or going down through the road. So that's one pair of forces that are balanced. But we also know it's going at a constant velocity, which means any backwards forces here have to be matched by any forward forces. So backwards forces here could be due to something like drag, air resistance, friction. So if you look at all the sort of force of friction there and drag, air resistance, whatever, that's going to pull it backwards here. Okay? So for the car to travel at a constant velocity, we must have a forward force occurring that's going to balance that. So if we look at that forward force that's going to balance that backwards friction there, there's going to be an equal force coming forward here. Now a lot of people will tell you that's the force of the engine, and so they'll just label it the force of the engine. The reality here is that the engine is actually going to turn through the crankshaft here, the tail shaft to the wheels. That's going to cause the wheels to push backwards against the road because of friction, the friction force here. And the reaction to that friction force of the wheels pushing the road backwards is that the road pushes the car forwards, and this is the one we're labelling as F engine. But really it's a reaction to the road being pushed backwards by the wheels pushing back against it. Okay? So just bear that in mind. But again, this forward pair of forces here and backward pair, the forward and backward pair of forces there are actually equal and opposite. So you're going to get the same thing here. The force, and you could call it engine if you want, but you should probably explain it, is going to be that way. That's going to be equal and opposite to the total friction forces or drag forces going backwards there as well. Okay? So that's a pair, that's a pair. So that's what's happening at a constant velocity. And I've got notes on this that I've put on there that people have been looking at. And you can actually word it there. The engine forces the tyres backwards against the road. The road exerts an equal force forwards on the tyres, pushing the car forward. I've called it engine, but it's probably not a good name for it. As the car speeds up, the overall drag friction force on the car increases. And obviously, you're going to get back to a steady speed again. So that's an aside there, really. Now, and it's still going to be equal and opposite as an overall force horizontally. So you're going to get no net force, constant velocity because of no acceleration. Okay? So if we go further down here, don't forget the downward force due to gravity here is going to be balanced by the equal force going up called the normal force, which is always 90 degrees up out of the road. Okay, so that's what that situation. The second situation would be what happens if you get a car going around a corner here. Now, in addition to the forward forces that are going on, the backward forces and the up and down forces, if you look at this from above, there's an additional force towards the centre of the circle because this is following a circular path at a constant speed. So it needs a force for centrifugal acceleration. That's towards the centre at right angles to the velocity. And in this case, it's provided by friction between the tyres and the road. If you remove that force, you will not get the centrifugal acceleration, and it will basically move off and go off a tangent, slide off the road there. So that's the second situation. What happens if it goes around a road that's a flat road but around a circle? Okay, it's going to go towards the centre of the circle, and that force is provided by friction, providing the centrifugal acceleration, as it says there. Now the last situation, the application, is probably the trickiest one when you're looking at can you use banking here to actually help basically. So you want a bank curve help you get around the corner. So you've got a bank curve one. So we're going to go around a corner there on a bank curve here. So he's going to try and go around a circle, right through here in a circle, but use the banking to actually help you do it. So when we're doing that, redo. When you're doing that one, I'm just going to draw a little box there for the car, make it a bit easier. There are still two forces acting on this car that we're going to worry about at the moment. So I'm not going to worry about the drag force or the engine force. We're going to just worry about the force of gravity on this. So we've got a gravitational force which is going to act down. So we'll draw it like that. So you get gravitational force going down there. And there's also going to be a normal force going 90 degrees, it's always at 90 degrees up through the road. Okay, so it's going to be 90 degrees there, go like that, 90 degrees here, that's 9, and this is actually going down. So this is the force of gravity, this one coming down here, okay, and you've got the normal force here, Fn, coming out of the road at 90. So I've got those roughly the right length, not exactly. So if you were to try and do the vector sum here of those two real forces then, and you drag this down, I don't know if I've got it exactly right, the vector sum of the normal force and the gravitational force, and this needs to be a bit longer actually, I'll draw a bit longer, that would be the vector sum of them. So to work it out, you would normally do tip to tail, and it would go from the start to the finish like that, and you would actually be able to draw your double arrow there. There's your net force there now. So I'm just going to move some of these things here. So the normal force that acts up through the road is going to be down here now. That's the normal force. When you add that to the gravitational force, you get a net force there, or a total force, towards the centre here. Now that's towards the centre of the circle. So that overall force can act as a force to supply the centrifugal acceleration to go around the corner. And if it's a steep enough angle here, it can supply enough of a force that way, in towards the centre, to supply all the centrifugal acceleration needed without the need for friction, which is really handy on roads where you're coming off a high-speed highway, which might sometimes be icy. The ice will prevent the friction, but this would do the job for you, because you're going to get a push inwards from the actual banked force there. All right? And obviously the steeper you make the bank, the more you're going to get out of that. So if you make an even steeper bank, you're going to get an even bigger force pushing you towards the centre, you'll find. So the angle can be pretty important to just determine whether you can go around a corner without the need of any friction at all. All right? There's another way of looking at this. So we've got two forces acting here. And if you look at the normal force now, you can break that up into components here and actually draw it as having a vertical component there, like that. And that component there, the vertical component of the normal force, will be equal and opposite to the force of gravity there, the weight of the car. That one going up is equal and opposite to the one going down. Because the forces are balancing here, you can look at this as a bit of reaction to the gravity there. But the overall force is zero because it's not going up off the road or down into the road. You've also got a force here, which is the net force going towards the centre here. And that's our net force. Now that's the horizontal component. And don't forget, that's actually going to supply the force for our centrifugal acceleration. So bear that in mind. This angle here can be shown to be the same as that angle in that triangle. Now from that, you can actually come up with a relationship between the angles there and the sort of force you'll need for a certain speed. But the relationship is this one here, tan theta equals v squared over rg. So it depends on the speed the car's going at, or the object's going at, the radius of the circle it's going around, and gravity. Okay. So how do you get that looking at this diagram? Well, if you start with tangent theta here, it's the opposite force, which is the horizontal force, over the adjacent force, which is the vertical one. And we've just said the horizontal force here is going to supply all the force for centrifugal acceleration. So that's going to be mv squared over r for A substituted in. So you can use mv squared over r, which is the one you've been using all this week. And on top of that, the force here vertically is matched by gravity. And that's just ma, or mg in this case, of gravity. And we've got mg there. And if you cancel those out then, mg there, you can see you'll end up with v squared over rg, and that's the relationship. So for any given speed here, at any given radius of the circle, you can work out which banking angle you need to use so that no friction force is needed. Sometimes I'll tell you the angle of the bank and say, based on that, for a certain radius, what's the maximum speed you can go around the corner without needing friction? So we're going to practice some of those. Thank you.